Okay, so today, our last lesson of rational functions. Today, it's kind of a disjointed topic. Usually, I like to end a unit by working backwards and actually creating a function versus solving a function and graphing it. So we will be doing that. But also would like just to take a little bit of time to focus on what do we do when our graph has holes in it, because I don't feel like we are all strongly confident or even moderately confident. So I want to readdress that. Okay, so your instructional objective, you can write rational functions that satisfy given conditions. Like I said, we'll be working backwards to make that happen. We've done this before. And I can write rational functions. I can graph rational functions with holes. So let's start off with writing some functions. Now, we're going to reverse everything we do in order to get these functions written. Typically, we start with a rational function in its general form, and we get the horizontal asymptote, we get the y intercept, then we factor it into factored form so we can see our zeros and our vertical asymptotes. Well, this time I'm going to start with all of the horizontal asymptote, the vertical asymptote, the zeros, maybe a point. And we're going to take and put all that information into factored form, and then we will simplify factored form and put it back into general form. So we're going to work backwards. Okay, so here's what I'm doing. I'm color coding. My horizontal asymptotes, we have two choices here, and I'm doing that in blue. If y equals 0, that means we are on the hunt for what is the lead coefficient A. We need to find it. So if y equals 0, we have to find A. If y equals some number, then we know the lead coefficient is A. Okay? We know it. So that's horizontal asymptotes in blue. In red, of course, red for restrictions. Those are our vertical asymptotes. Those belong in our denominator. I will be doing our X intercepts. I'll scoot my screen over a little bit. Maybe it'll let me. I don't know. Our X intercepts or zeros, they belong in your numerator. I'll do that in purple. And then if we have any other points, like say, for example, we don't get A, we get a condition or a point instead, I will do that in green. Okay? So here is the factored form of a rational function. It looks like this. Color code. This is your y, your f of x, equals your a in blue. And then there's all your linear factors, x minus c, x minus d, x minus e, x minus g, with your zeros in the numerator in purple and your restrictions in the denominator in red. I can say colors, red. And then I added one extra thing. If your graph has a hole in it, there will be a duplicate factor in your numerator, linear factor in your numerator and denominator. So I just labeled it x minus the hole over itself, because that's the situation where we're going to actually simplify the fraction, which creates a removable discontinuity or a hole in our graph. So you got that color coded? You ready to go? Ready? All right. So here we go. Here's what we're going to do. I'm going to do A with you. Then you're going to do this problem. Then we're going to come back and do B. Okay? So let's start with A. My first piece of information, my given condition, we're going to write the equation, is the vertical asymptote, which I do in red. And there is 1. So I'm going to write it in its linear factor, which is x minus 4. And that belongs in our denominator. Okay? Then I'm switching. The next piece of information is my horizontal asymptote. And it's y equals a number that's not 0. So that means that I know what A is. A is the lead coefficient, -1. If I divide numerator by denominator, those lead coefficients, I'm going to get -1. That also tells me that my degree of the numerator is the same as the degree of my denominator. That's what that tells me, because it's not y equals 0. So degree, same in numerator, denominator. Then I'm going to switch to purple to find my x-intercept, also known as my 0, right? And so I'm going to write its linear factor, x minus 3, and that's going to go in the numerator. Okay, so that's all of the given conditions that I have. I have A, I have my numerator, I have my denominator. So here's what I'm going to do. F of x equals, all right, I'm going to pick up my blue pen and insert my A. Then I'm going to switch to my purple pen, and I'm going to insert my 0, x minus 3, in my numerator, and I'm going to insert my restriction red pen in the denominator. And then we're going to see if that satisfies conditions. Is the degree of my numerator the same as the degree of my denominator? Yes. So we're going to finish this problem out. So we have it in factored form, but that's not the equation I'm looking for. I'm looking for it in its original form. So let's simplify it. So we get -x plus 3 all over x minus 4. And before you decide you're good with that, I do want to talk to you about one other thing. So I'm going to show you how to plug this into Desmos just to make sure that it's correct. I'm going to pause the video for a second. Okay, so here in Desmos, I typed in the equation that created. I also typed in my horizontal asymptote and my vertical asymptote, just so that I can see if my graph really is fitting the description that fits in the asymptotes. Do you think that looks good? Yeah, it looks really good. And just so you know, if you're not sure, you can, when you highlight or just hold over that little icon, you can change it from a solid line to a dotted dash line to a dotted line, just so that you can see your asymptotes. And you can type all of your asymptotes in there and just make them dotted or dashed so that you can just verify your work, that it's good. Okay, so I just wanted to note that. You might want to write that down on your note page. Okay, back to work. You try this one. P.S. It's got a hole in it. So let's see how you do. I'm going to pause the video, give it a try, then come back and see how you did. Okay, so hopefully you've got it down to this position where you have included the situation where you have a hole, which is a duplicate factor in the numerator and denominator, and your hole's at 0. So x minus 0 over x minus 0, which reduces down to x minus x, which I inserted in the front because it's a monomial factor. Okay, and then you have your A and your x-intercepts and your vertical asymptotes. Let's go ahead and simplify that. Now, typically when I simplify these, I will not distribute my monomial first. I'll multiply my binomial pairs, and then I'll distribute. You can, of course, do it however you like. But I'm going to go ahead and multiply that. That's x squared. Then I'm going to do a little outer inner multiplication. So -4x minus 1x is -5x plus 4 all over x times. Same thing again. I'm going to go ahead and multiply out this binomial pair. X squared. -5x plus 2x is -3x. And 2 times -5 is -10. All right. And then I just have to finish this up by multiplying or distributing to clear the parentheses. So 2x cubed minus 10x squared plus 8x all over x cubed minus 3x squared minus 10x. And there you have it, worked backwards. And hopefully it's starting to make some sense. Okay, so now we're going to go to this last problem that's just a little different. So let's pick up our colors again. We first have vertical asymptotes, which we do in red. So let's go ahead and write out those factors. Which one do you want to do first, x plus 3 or x? So we'll do x and then x plus 3, right? Because it's x minus negative 3. Okay, so there's that. Our horizontal asymptote, something's different. Y equals 0, which means I don't know what A is. I'm going to have to actually algebraically find it. I know. What a pain. Okay, then we have our x-intercept or our 0. So that's the factor x minus 1. Now here we're going to need our green pen because we have one more condition. The f of 2 is 1. 2 represents our x. 1 represents our f of x. And so we have to have at least 1 point if we're going to find A. Okay, so I'm going to go ahead and just set up my plan here by grabbing my pencil and doing all of the things. I have an x-intercept in my numerator. I just have one, so I'm just going to go ahead and put the one linear pair in my numerator. I do have the 2 linear pairs in my denominator, which would be an x times an x. I'm just going to put a minus there. I'm going to go in with my red pen and change that. So I don't know what A is, so now I'm going to go and grab my blue pen and I'm going to insert my A. So that's what I'm looking for, and I'm going to have to solve algebraically by plugging in all of the other pieces of information that I have. So I'm going to start with my green pen and replace my f of x with 1 and put a 2 everywhere I would insert an x. So 2 there, 2 there, and 2 there. And then I'm going to grab my purple pen real quick. Purple pen. I'm going to insert my x-intercept or my 0. Then I'll grab my red pen and I'll insert my zeros. I'm sorry, my vertical asymptotes, my restrictions. So that's plus 0 or minus 0. I'm not even going to write it there. And then minus 3. So minus negative 3. Sorry, it's minus negative 3, so plus 3. So I have everything but A inserted into the equation. We're going to solve algebraically. Let's simplify first. 2 minus 1 is 1, and that's 2 times 5, which is going to be 10, right? So we get 1 equals 1A, I'm just going to write A, over 10. So we can solve for A here by doing what? Yeah, clearing the fraction. Multiply both sides times 10. So A equals 10. So now we know what A is. We can now write our equation. And so we'll go back and then remove the f of the point that we plugged in for x and f of x and reinsert our f of x and x. So we'll have f of x is equal to 10 times x minus 1 over x times x plus 3, just reinserting all of our values that we found earlier up here, right? Putting the x and the f of x back in. Then all we have to do is simplify, correct? And we will have it in general form. So 10x minus 10 over x cubed, not cubed. Try that again. How about squared plus 3x? And again, you can trust me on this one, but when you're doing this for your homework, of course, use Desmos just to double check your asymptote, that the graph fits inside the asymptotes and actually passes through to 1. Okay, questions? All right, so here's what we're going to do. Flip it over on the back. We are going to start with problem 1, and here's what I'd like you to do. I would like you to take a moment to type this equation into your graphing calculator because I'm going to ask you for some information. So I'm going to pause the video for a moment. All right, so now that you have that plugged into your calculator, let's start with getting all of the information from the original function before we factor it into its factored form. Let's start with our horizontal asymptote. Let's see if one exists. Same degree? Yes? So our horizontal asymptote then is, what is x squared divided by x squared? 1. Okay, so there's our horizontal asymptote. Let's go ahead and graph it. And this graph has got a hole in it. Okay, so this equation is going to simplify down to a linear over a linear polynomial. So it'll be a really basic graph. So we don't have to worry about the scale. We'll just stick to the scale that's on the graph. All right, so label that y equals 1. There's our horizontal asymptote. And then switch to your purple pen. And let's get our y-intercept, which is also readily available here on the end. Our y-intercept is, you got it, negative 1/3. That's what we get when we put zeros in for all our x's. So negative 1/3, we'll go ahead and graph that too. Beautiful. So that's what we can get from the general form of the equation. Now let's factor. So I'm just going to pick up my pencil to factor. All right, so f of x is equal to, let's factor it out. Factor in your numerator into binomial pairs here. X plus 1, x plus 2, I like it. Yep, that definitely satisfies the conditions. Multiplies to 2, adds to 3. Let's also factor the denominator. Looking for the factors of negative 6 that add to negative 1. Wouldn't it be x minus 3 and x plus 2? And listen, we're in search of a whole. That's what we are focused on for this last objective. Do we have one? Right here. So let's find our restrictions real quick. We know that we are restricted. X cannot equal negative 3, positive 3, and x cannot equal negative 2. But when we go to simplify this, the negative 2 becomes a whole. So we have a hole in our graph where x equals negative 2. But we need to know where does that, because it's not an asymptote. Okay, because we're about to simplify this fraction. We do have a horizontal asymptote at x equals 3. So let's go ahead and graph x equals 3 as our vertical asymptote there. What? Oh, thank you, vertical. Thank you, that was an easy fix. Woo, thank goodness. I'm going to scroll down here real quick. Not that far. Come on, cooperate. So there's our vertical asymptote, x equals 3. But the other one, negative 2, isn't an asymptote. It's just a hole in the graph. So I'm going to go back, and I'm going to simplify my function by canceling out the common factor. So x plus 1 over x minus 3. So let's focus on that. We need to find the other part of the whole. This is the equation that we are graphing. We are graphing this equation right here. But it came from this equation, which has a restriction where x equals negative 2. Does this equation have a restriction at x equals negative 2? No. But this equation is the simplified version of this equation. So we have to figure out where's the hole. So what do? Do we plug negative 2 into the original? No, because that'll create a 0 in the denominator. Do we plug it in factored? No. Do we plug it in reduced factored? Yes. So we're going to do negative 2 plus 1 over negative 2 minus 3, which I believe is negative 1 over negative 5. So our hole is at negative 2 1/5. So let's go put a hole in our graph at negative 2 1/5. It's a little high on my paper, but you're good. Listen, there's one other thing we have yet to find. What is it? What? The x-intercept. We need to find the 0, which we can get out of the numerator right here, right? Yeah. So we have a 0 at x equals negative 1. So we'll go ahead and we will also graph that. But we don't have a 0 where x is negative 2. Because we're not allowed to do negative 2, remember? Okay, so that's what I got so far, and that's as much as I can get from my equation. Now I need a table of values. And we don't have to be crazy about the values that we pick. Let's just pick negative 10 to see what our graph tends to do on the left. Let's approach 3 from the left, so we'll pick negative 2.99, see how that does. We'll approach it from the right, our vertical asymptote. and then we'll get 10. So I'm going to need you to give me values with your calculator because I don't have it done. So somebody give me, what is the f of x for negative 10? 9/13? Did you say that? 9/13? Is that less than 1 or greater than 1? Less than 1, so it's down here somewhere, right? All right. Then 2.9999, I'm thinking it's pretty negative. What is it? Negative 399? Check your math. That's not going to work. 3,999. That sounds right. Okay, so here's what I know this graph is doing. It's starting way up here, hugging the asymptote, reaching your removable discontinuity at your hole, and then graphing, cruising through those 2 points there. It's not a very good graph. And then it shoots way down to infinity, negative infinity. So that's behavior there. What happens when we plug in 3.001? 4,001, so that's way up high. And how about when we plug in 10? 1.57, so 1.6, so that's like right there. And then we can't even graph that other number, it's so big. Just keep it looking fairly similar, get the tendency of the graph because you know that's what I'm concerned about. You've got all the critical points graphed. You've telling me what's happening on the asymptotes. I'm not going to ask you today to describe all the end behaviors. I just want you to focus on what do you do when you have a hole in the graph. Okay? Questions? Okay, then here's your chance to show me you get it. So I'm going to pause the video while you work out this problem, then come back and see if you've got it correct. Okay, so found a horizontal asymptote at y equals 0 because our numerator's degree was less than our denominator's degree. We found our y-intercept at negative 1/3. We factored and found a hole at x equals negative 2 again. So our simplified version was 1 over x minus 3. There was no 0 in the numerator left, so no x-intercept. Vertical asymptote x equals 3 and a hole at negative 2, negative 1/5. We plugged in a couple values after we drew our graph. You got your critical points in there. And you can see that this graph is very similar to the last one that we did. Maybe just shifted down one space, but there you go. So that's graphing when you have a hole. So problems for your homework are 35 through 37 and 41 through 44. Also, just for those of you who weren't here today, your review for the test that's coming up on Wednesday is on Canvas. It is part of your homework. Do your review.